Welcome everyone to the lecture on catalytic organometallics. This is of course part 1. And let's start with a nice reaction from stoichiometric organometallics. As a model compound, research group of Barry Martin Trost at Stanford University was in need of this for synthesis of this compound. Well, this is not a benzene ring, this is a cyclohexane here. So, and the best method for synthesizing such an enone and also a lot of other ketones is, of course, starting with an acid derivative with a leaving group X. Well, and letting that react with an organometallic nucleophile, as we have discussed it the preceding lecture on stoichiometric organometallics. So, in this case, we would like to treat this acid derivative with an alkynyl lithium compound. Well, if we have an ester here, an alkoxy leaving group, then we would have the problem that after the reaction of the first equivalent of alkynyl lithium compound, we will have a ketone, an alpha beta unsaturated ketone, and this ketone is more reactive, more electrophilic than the ester, and we would get then the double reaction as the competing reaction. Well, you can avoid that a bit by applying the acid chloride, because the acid chloride is more reactive than the ketone. However, the best method seems to be the one having a special amide. The methoxymethyl amide, and in this case we would get as a reactive intermediate the addition adduct this one with the lithium chelated. This is rather stable at least at lower temperatures, and well, will just survive the normal reaction conditions. And after hydrolysis, we will get, of course, an NO hemiacetal, which then at room temperature will just be hydrolyzed. That's it. And the final outcome is then this ketone, which can be isolated in an astonishing 97% yield. This method, applying the amides of this methoxy substituted amine, is called the Weinreb-Nahm ketone synthesis. Under this name you can look that up. So, what was then done with this alkynone in the Trost group was treating that with a palladium catalyst, 5% palladium acetate was applied, 35% triphenyl phosphine were present. Also possible, instead of a triphenyl phosphine, are other phosphines. For instance, DPPB was tested. So, what is DPPB? It's the abbreviation for 1,4-bis diphenyl phosphino butane. So, the B is the abbreviation for the butane. So, structure of that should be clear for everyone. It's this one. Another phosphine that has been applied was the DPPF. Well, okay. DPPF, then the F abbreviates ferrocene, and you know this is that iron sandwich. Compound, this time as DPPF with 2 phosphino substituents. So the reaction which was observed works with any phosphine ligand, while adding about 50% an acidic co-catalyst, in this case just acetic acid, helps to accelerate the reaction. And well, you need a solvent that was toluene at 100 degrees. The product that was obtained was then a diene known, this one, 90%, well, based on GC analysis, but between 70 and 80% actual yield on a small scale process was obtained. And usually with enlarging the scale of a reaction, you can isolate a bit more of that, a higher percentage of that. So that means the reaction which the Trost group observed was an isomerization. That means, well, a double bond part is migrating to this position and that, and to that. Okay, and of course, the dienone is thermodynamically preferred compared to the alkynone. So, let's try to explain the mechanism of the reaction. It has a lot, the anticipated mechanism has a lot of typical reaction steps, at least of palladium catalyzed processes. All the active palladium catalyst which we need for this reaction seems to be a palladium 2 complex, but a hydrido palladium acetate. And how should this be formed? So we start with palladium acetate and under the reaction conditions, typically palladium acetate, or often palladium acetate, is reduced from palladium 2 to palladium 0. So let's assume 2 ligands, in this case phosphine ligands, are added. Then we get to palladium 0. We will discuss in detail how this reaction works. And in the equilibrium, acetic acid is added to the palladium, and we get this hydrido palladium acetate in the oxidation state +2 again, which then will react with the substrate. So, how does this reduction work? A lot of organic compounds are able to reduce palladium acetate or also palladium chloride and other palladium 2 salts to palladium 0. This is, for instance, possible with some olefins by an addition to the olefinic double bond and then beta hydrogen elimination. We will see examples of that during this lecture course. In this case, it's obvious we have phosphine ligands, and these phosphine ligands are the reducing agents. What will be the product of the oxidation of these phosphines? Well, clearly phosphine oxides. So, how does this reaction proceed? Palladium acetate plus 2 equivalents, for instance, of triphenyl phosphine, gives the corresponding complex. Actually a coordinatively unsaturated 16 electron complex. Tomorrow we will discuss that 16 and 18 electron complexes. And for instance, in DMF at already room temperature, the reduction occurs. Well, and it is initiated that this complex falls apart into this palladate, and on the other hand this phosphonium compound. Now imagine a hydrolysis, and since you have only catalytic amounts of the palladium acetate in there, you only need very small amounts of the water. So, water and another equivalent of triphenyl phosphine will result in a palladium 0 just coordinated with 2 phosphine ligands. So a coordinatively very unsaturated 14 electron complex, which is very often an active catalyst, for instance in the Heck reaction, which we also will discuss tomorrow. And, well, what else do we have? Triphenyl phosphine oxide as the stable oxidation product, and, well, 2 equivalents of acetic acid. So, here we have the palladium 0 complex corresponding to this, well, L2 palladium 0, adding acetic acid, giving rise to the active catalyst. So, let's have a look at the reaction in focus. Once again, the substrate. Plus the hydrido palladium acetate. First step, which was suggested by the Trost group, is a typical step of in a lot of similar reactions. It is hydropalladation of a triple or a double bond, well, which should remind you of a hydroboration. This is very similar. So a hydrometallation, as always, proceeding as a syn, concerted syn addition process. So one could also discuss the reduced selectivity of that addition process. However, for the observed outcome of the reaction, we need, as the next step, a beta hydrogen elimination. This is essentially the retro hydropalladation, the retro process compared to the hydrometallation or hydropalladation in this case. It is also a concerted process, and it is a syn elimination. Well, this is not that important in this case, but the syn elimination to one of those hydrogens will then lead us to an intermediary alene which has the palladium generally still coordinated. While in equilibrium, this could be, the alene could be set free. However, in this reaction, the alene has not been observed. This seems to be rather highly reactive for a re-addition of the hydro-palladium bond. However, I should mention that indeed, in this case, the beta-hydrogen elimination is a bit strange or a bit unusual. If the palladium is located at an sp3 hybridized carbon with a beta-hydrogen, this is usually a rather fast process. If that hydrogen and the palladium can adopt Syn conformation. With the palladium sitting at an sp2 hybridized center, this is an unusual reaction. Well, although there is at least one example known where an alenic product was observed, but in this case with cesium carbonate, special base with special effects in that case. However, here it is claimed that this also works, giving this intermediate and the re-addition reaction should then give this allyl palladium complex, and now the beta hydrogen elimination with the palladium sitting at an sp3 hybridized center should be rather fast. Again, setting free the active catalyst and the final product, which indeed has been observed as reported from a Trost group. A few months after these results have been published by Barry Trost from Stanford University, another group from University of Shanghai published that they independently found the same results, and they studied the reaction in detail also with other metals as catalysts. Well, we found that also iridium, rhenium, ruthenium, rhodium complexes can catalyze this reaction. And well, let's have a look for some of their experiments. Okay, here you see their model compound with a bit longer chain here, a longer side chain. They applied just 1 mole transition metal catalyst, found out that it is sufficient. And as you see here, an iridium phosphine complex, 99% result, also with an rhenium phosphine complex, also ruthenium. Well, with this iridium COD complex, COD is the abbreviation for cyclooctadiene, and with ruthenium chloride hydrate, well, they didn't get any of that product. So it seems to be important that you have a phosphine complex. And indeed, they tested that if you add more ligand, 16 equivalents compared to the catalyst, for instance, then the yield, or the conversion here in this case, we also did just a GC analysis, the conversion indeed increases significantly. Well, actually, this is a bit strange. So, as we know, normally you need an coordinatively unsaturated transition metal complex as the active complex. And therefore, having a huge excess of the phosphine ligands should generally slow down your reaction. This is what we should keep in mind if we try transition metal reaction. And this is an unusual example, indeed, because this claims that it is the opposite in that case. Well, okay, about 2 years later, in 1992 or 1993, there was a new postdoc in the Trost group, Uli Katzmeier, who I know very well. He is now professor at the University of Saarbrücken. And what he did is something very important. He did some blank tests and found out that you can just skip the transition metal salt. You just need the phosphine. So actually this is not a transition metal catalyzed reaction at all. It is a case of organocatalysis, where small organic compounds catalyze the reaction. So we have obviously to revise the mechanism. So let's have a look to the revised mechanism. Nevertheless, discussing that makes sense because these are indeed typical reaction steps which we will see throughout the next parts of the lecture. So, what is the revised mechanism after Uli Katzmeier found out that you don't need the transition metal? Obviously, there is the direct interaction of a phosphine, because you can also apply other phosphines than the triphenylphosphine, just abbreviate that also substituent is R. So you need a direct interaction. You have the free electron pair at the phosphine, and it will, of course, attack as a nucleophile. Could be here or there. Well, hard soft acid base principle, it should preferentially attack at the electrophilic better position. And all reaction steps are in equilibrium. So, if we now protonate in equilibrium, and this explains you need these protonation and deprotonation step in that mechanism. This explains why a bit of acetic acid accelerates the reaction. So you will protonate here, and the enol will be transformed to the ketone. So where will a deprotonation take place? In close proximity to the phosphonium cation, and in conjugation, these protons are rather acidic. So, protonating again, why not a second time here, getting to a ketone again. Next step is again a deprotonation. Of course, a deprotonation could lead us back to here, but since this is an equilibrium, it will react in this direction. It also will react in another direction. Here, this position also becomes somewhat acidic. If we deprotonate here, what do we have as an intermediate? In this case, we have a conjugated ylide as an intermediate, as we know it from, for instance, Wittig type processes. So now imagine that we deprotonate the ketone at this position and reprotonate here. So it's just a transfer of a proton from this position to that one. So then we have again an enolate, and here a phosphonium as a good leaving group. And indeed, the phosphino group leaves the molecule, and, well, this is then the formation of the final product. I think it's a nice mechanism, and for some other examples we will discuss soon, it's important to notice that alternatively to deprotonating here in this position, a nucleophile could attack plus a nucleophile with an anionic charge, And this allows us to introduce substituents that get into the molecule as nucleophiles. Numerous applications have been found for this type of process. Well, what already Uli Katzmeier did during his postdoc studies was testing if also allenes will be isomerized by phosphine catalysis. Well, and indeed, triphenylphosphine, toluene, just 60 degrees, 2 hours reaction time. Isomerizes the allene to the corresponding diene system. Well, 90% yield was obtained, isolated yield. So, now 2 examples. There a nucleophile is introduced. So, if we compare that with the starting compound, so where is the nucleophile introduced? Alpha, beta, gamma position, to the gamma position of the original starting compound. So this is the alpha, the beta, the gamma position. That means the nucleophile is introduced here. This becomes sometimes during the reaction an electrophilic position. So since this is acidic here, this is normally regarded as potentially nucleophilic. That means this phosphine catalysis effects an Umpolung of reactivity in this position. So, first example. An alkenylic acid ester, alpha, beta, gamma position. The nucleophile will be introduced to that position. And again developed in Barry Trost's research group. This is a typical nucleophile. If you deprotonate that melanate then. So, and 35% triphenylphosphine, 50% of an acetic acid, sodium acetate buffer. Once again, toluene as the solvent, 110 degrees, 20 hours reaction time. So, and as I said, the nucleophile is introduced to the gamma position, while the alkyne is again transformed to an alkene. And this product was isolated with 59% yield. Another interesting example. Now, DPPP was used as a rather good catalyst. So what is DPPP? So B, abbreviated butane, F, ferrocene, P, just propane. E would be ethane diol bridge between the two phosphenyl substituents. It's this one. So, as a result, a spirocycle was obtained. The oxygen of the hydroxyl group will work as the nucleophile, and this nucleophile again attacks at the gamma position, alpha, beta, gamma. So an oxygen-carbon bond is formed here. Okay. And therefore, it should be clear that this is the anticipated product which was indeed obtained. So what is the clue for applying that bidentate ligand? Well, as a reactive intermediate, you should have sorry. This one. 1, 2, 3. Okay, and here you have the second phosphenyl group with a free electron pair, basic, and just deprotonating. Attacking as a nucleophile here and effecting the formation of that billet as reactive intermediate. Well, I don't have the yield obtained in this case, but it was also in the range of 60 to 70%. Other groups became interested in this type of process. For instance, Gregory Fu group at MIT. Here's an interesting example from Fu's group. He used 50% of benzoic acid and 10% of the phosphine catalyst. So, and this is the product we should anticipate for also from already from Trost group results. So, what is new from Gregory Fu's group? Well, they optimized it for enantioselective synthesis. They obtained this product enantio selectively with an 82% yield and 94% enantiomeric excess when applying a chiral phosphine a spirocyclic and a trope chiral phosphine. Not that easy to draw, and this should be the S enantiomer. So let's go on with a bit more complicated example from Ikuyoshi Tomita's group from the Tokyo Institute of Technology. So he chose to apply this type of substrate where we have an alkynone, typical for the reactions we already discussed, and now in the side chain intramolecularly a functionality. Applying 20% of tris-N-butyl phosphine, THF, at reflux temperature, I think. He obtained up to 70% of products of this type. Racemic. However, these are, of course, interesting structures. So, let's think about what happened here. Well, at some stage of a reaction, an aldol addition step has obviously taken place. So, the mechanistic interpretation follows what we have discussed before at the Trost example. So, the phosphine attacks as a nucleophile. Let's stay with the butyl tributyl phosphine. Here we are. Here we are prime substituent. Again, protonating at this position will lead to the ketone again. So, the ketone should be acidic in alpha position. Well, it is already acidic there, but the acidity will increase since the whole molecule is positively charged. So, deprotonating here, and then intramolecularly attacking the carbonyl group in the sense of an aldol addition step. One, two, three, four, 5 position. That means we will build up a 5-membered carbocyclic ring. So, and now, let's put a minus charge here. Now this is the position to attack with a nucleophile that we get the ylid formed. Deprotonating here, protonating there, means setting up the system for eliminating the phosphenyl group, the phosphonium group. Yeah, well, okay, and that's all. Setting free the active catalyst. Finally, let's try an exercise. Again, Gregory Fu thought, let's modify this type of process. And having an alpha-beta unsaturated ester offered intramolecularly. %20 of a phosphine as catalyst, again a bit of acid. And now it's your turn as an exercise. Please figure out the structure of a product. So let's compare the substrate with the one we have studied before. So it's very similar. Actually, it is always same, except that this oxygen has been replaced by that carbon, CH, and here that ester sitting there. Okay? Well, okay, and R prime changed to an hydrogen. That's it here. So, that means, in principle, we could draw here the product which we have seen before. but not with an oxygen there. Having hydrogens at this position. And now again, let's exchange the oxygen here against a CH group. And at that carbon, the ester group is also sitting. Oh, that's it. So, and of course, the Fu group again applied their chiral phosphine and therefore achieve chiral induction. And this one was the product they obtained, well, with a moderate, but nevertheless nice 60% enantiomeric excess. So, this was a small journey to organocatalysis, and I promise tomorrow we will go on with real transition metal catalysis. Thanks for listening. See you tomorrow.